I'll try to illustrate the conceptual meaning of the Bernoulli equation with this example. So we've got a pipe here carrying fluid from left to right. Suppose fluid is entering over here and exiting and going off over there on the right. The pipe is changing in diameter and also changing in height. X is the horizontal direction, Z is the vertical direction. And in steady state flow, we can map the flow with streamlines. And so I'm showing three different streamlines here, streamline A, B, and C. Each of these would be a path that a particular tiny fluid element would follow as it moves in laminar flow through this pipe. So let's look at the exchange of pressure for kinetic energy, for gravitational potential energy as we move along one particular streamline. Let's pick streamline B in the middle here. You have to apply Bernoulli's equation to different points on this same streamline. It does not apply to points on two different streamlines. So we'll focus just on points x1, x2, x3, and x4 along streamline B. And here I want to graph the variations in pressure, gravitational potential energy density, and kinetic energy density along streamline B. So let's start with the changes in the gravitational potential energy density, since that's the one that is easiest to see from the picture. As we go from point 1 to point 2, the Z value has not changed, but then Z increases. We go up in height from 2 to 3, then Z stays the same from 3 to 4. So that means that the gravitational potential energy density is staying the same from x1 to x2, but then we see it increase as the pipe rises from x2 to x3, and then Z stays the same beyond that point. So the density rho and G, of course, are constant. So as the height changes, the gravitational potential energy density changes. Now let's work out how the other two terms are changing as well. To figure out how the speed changes, we'll have to make use of the continuity equation. So we note that the volume per second passing through any given gate, so passing by points 1, 2, 3, and 4, has to be the same in steady state flow. So we write that the product of cross-sectional area and speed at any one of those points all have to be the same. So A1 V1 equals A2 V2 and A3 V3, etc. So when cross-sectional area decreases, the speed must increase. In order to maintain the same flow rate everywhere throughout the pipe so that water doesn't somehow build up somewhere. So we can tell from our picture here then at points 1 and 4, where the pipe is wide, that's where the fluid will be moving slowly. But at points 2 and 3, where the pipe narrows, that's where the fluid will have to be fast. So we must be gaining kinetic energy as we move from 1 to 2, keeping it from 2 to 3, and then losing kinetic energy from 3 to 4. So that'll influence our graph here. To figure out how much kinetic energy we gain or lose, that's going to depend on how much the area changes by. So let's suppose that the cross-sectional areas at 2 and 3 in the middle, where it's narrow, let's suppose that those are half the size of the cross-sectional areas at 1 and 4, where it's wide. In that case, the speeds at 2 and 3, which we know are the same, those speeds at 2 and 3 are going to have to be double the speed at 1 and 4. Since if the cross-sectional area goes down by a factor of 2, then the speed of the fluid is going to have to go up by a factor of 2, according to our continuity equation. So then we can work out how the kinetic energy densities change. Therefore, 1/2 rho V2 squared, the energy density at moment 2, in that low, narrow section of pipe, that'll be equal to the kinetic energy density at moment 3, the high, narrow section of pipe. But at moments 1 and 4, where the pipe is wide and the speed is lower, let's see, there, V2, since V2 is twice V1, if we square V2, then we're squaring 2 times V1. So V2 squared would be 4 V1 squared. So we can write that this is equal to 4 times 1/2 rho V1 squared. And likewise, since V3 is twice V4, if we put in 2 times V4 for V3 and square it, then V3 squared is 4 times V4 squared. So this equals 4 times the kinetic energy density at moment 4. Okay, so the point is that if the cross-sectional area goes down by a factor of 2, the speed is going to have to go up by a factor of 2. But since in the energy, speed is squared, the energy goes up by a factor of 4. So therefore, as we move from moments 1 to moments 2 and 3, our kinetic energy density is going to have to go up by a factor of 4. So let's illustrate that. Our speed is going to change in this section where the pipe is narrowing. That's where the speed changes. That's our acceleration zone right there. That's where we'll speed up. And then here, this other acceleration zone is where we'll slow down, where the pipe widens out. And so let's now show the kinetic energy density going up by a factor of 4. So it is 4 times higher than it was at moment 1. Then from 2 to 3, it stays the same. Our speed stays the same from 2 to 3 if the cross-sectional area stays the same from 2 to 3. So you might guess that the fluid would slow down as it moved upwards, but that can't be the case. If the cross-sectional areas are the same, the speeds have to be the same in order to maintain that flow rate. So the fluid doesn't slow down as it moves upwards. We'll have to explain how it moved up without slowing down by talking about the pressure. That's going to explain how that happens. So we'll get to that in a moment. Past moment 3 is where we have this other acceleration zone where the fluid is going to slow down back to the speed it was at, back at moment 1. So we've got this story for the kinetic energy density increasing to the narrow section of pipe and then decreasing again to the wide section of pipe, which leaves us just to work out what's happening with the pressure throughout the pipe here from moments 1, 2, 3, and 4. Okay, we could probably sketch in that pressure graph just from knowing these other 2 graphs here, but let's take a moment to look at how you would use the Bernoulli equation in practice here. The idea is that you can compare 2 moments on one streamline and set the sum of 3 terms at moment 1 equal to the sum of those same 3 terms at moment 2. Here is that. Those 3 terms are the pressure, the kinetic energy density, and the gravitational potential energy density. Those 3 terms at moment 1 equal the sum of those 3 terms at moment 2 in order to conserve energy. And at moments 1 and 2, the z value is the same. So these two terms are identical. So we can subtract those terms from both sides. The fluid has not changed in height from moment 1 to 2. And then what we typically do is gather the difference in pressure on one side and the difference in kinetic energy density on the other side. So we could then write that the pressure at moment 2 minus the pressure at moment 1. The change in pressure should be equal and opposite to the change in kinetic energy density. The final value of kinetic energy density minus the initial value of kinetic energy density. So since we know how much the kinetic energy density changed by, we can determine how much the pressure changed by. And in fact, since we know that the fluid is faster at moment 2 than at moment 1, because the pipe narrowed, then this quantity is positive, which means this minus here means this quantity is negative, which means the pressure at 2 is lower than the pressure at 1. That's consistent with the Bernoulli principle that says that the pressure should be higher in a wide section and then lower in a narrow section. High pressure where the fluid is slow, and then low pressure where the fluid is fast. And that's what our equation here is telling us. Let's apply the Bernoulli equation again from moments 2 to 3 in the narrow section of pipe where the pipe is raising. From 2 to 3, we know the speed is the same since the cross-sectional area is the same. So therefore, this time, these two terms are equal to each other, so we can subtract them. They cancel out, and therefore write that the pressure at 3 minus the pressure at 2, this time the difference in pressure is going to be equal and opposite to the difference in gravitational potential energy density. So how is it that the fluid managed to move upward without slowing down? Well, what happened was, since Z is higher, Z3 is higher than Z2, this is positive, so this is negative, which means our pressure dropped again. It's the second pressure drop. Pressure at 3 must be lower than pressure at 2. So the fluid managed to increase in height without slowing down by decreasing in pressure. We have higher pressure here at 2 than at 3. The pressure dropped. This high pressure down here pushed the fluid upward, overcoming the tendency to slow down as you do the force of gravity. The high pressure here added a pressure force that overcame the force of gravity so that the fluid was able to maintain its speed while increasing in height. So we have a second pressure drop as the fluid moved upward to a higher elevation. I guess we could illustrate that here by showing something like relatively high pressure here compared to low pressure there. When a fluid goes to a higher elevation, the pressure drops. And then lastly, from 3 to 4. As we go from 3 to 4, we're at the same height at 3 and 4. So these two terms drop out this time. And we can therefore say that the pressure at 4 minus the pressure at 3, the difference in pressure is equal and opposite to the difference in kinetic energy density. So here, as the fluid slowed down, the pressure should go up. We lose kinetic energy density, but gain pressure to compensate and conserve energy. V4 is lower than V3, so this side of the equation is positive, so P4 is higher than P3. The pressure went up from 3 to 4. Low pressure here, relatively low pressure where the fluid is fast, and then relatively high pressure where the fluid is slow. There's the Bernoulli effect once again. Okay, so we could use all that to graph what happened to our pressure here. So let's go back and finish our sketch. Let's see. We could note that since the sum of these three values has to be the same at all times, that let's see here at moment 1, our blue function is at 1 unit, the green function is at 2 units, and the red function is at 6 units. So 6 plus 1 plus 2 is at 9 units total. So it has to be 9 units total at all times. So here we have 2 units for the green and 4 units for the blue. That makes a total of 6 units. So the pressure must be down at 3 units. So the pressure must have dropped down to this value in that acceleration zone here where the fluid was speeding up. Then the pressure stays constant in that lower narrow section of pipe, but our pressure has to drop again as we head towards the higher section of pipe. So here we've got 1, 2, 3, 4 blue units and 1, 2, 3, 4 green units, which leaves only 1 unit for pressure. So the pressure must drop down to this value. There's our second pressure drop as the fluid increases in height. But then at the end here, the pressure will rise once again. It'll have to go to this height so that the sum of 1 unit plus 4 units plus 4 units is 9 once again. The sum of those three terms is always constant. Here's one more way of illustrating that. Same pipe, same scenario, but we could use this sort of bar graph depiction here for the exchange of these three terms across streamline B from moments 1 to 2 to 3 to 4. 1, 2, 3, 4, 6. Yeah, we've got 9 boxes here. So this bar graph thing would show that we've got this much pressure at moment 1 and this much gravitational potential energy at moment 1 and this much kinetic energy at moment 1 according to this our function over here. Why don't you take a moment and fill in, color in these other three bar graphs for moments 2, 3, and 4, showing how we exchange red for green for blue, but keep the same total amount at all three times. Go ahead and pause the video and color in those other three bar graphs. Got the result? Should look something like this. We gain kinetic energy heading into 2. We keep that kinetic energy in 3, but we lose that kinetic energy going to 4. As the pipe got narrow, we sped up. Then the pipe got wide, we slowed down. We stayed the same height at 1 and 2, so still 2 units. But then from 2 to 3, we gained in height, so we gained gravitational potential energy up to 4 units, and we kept those 4 units of gravitational potential energy from 3 to 4. So we dropped in pressure from 6 units to 3 as the fluid sped up. We dropped in pressure again from 3 units down to 1 as the fluid gained elevation, and then we increased in pressure as the fluid slowed down from the narrow pipe to the wide pipe. Bernoulli's equation says that a moving fluid element exchanges pressure for speed for height.